Hi everyone and welcome to EE 323 Lecture 6. Today I'm going to be introducing the concepts of IC design philosophy. Also going to be talking about current mirrors. You can find both these topics in your book in sections 8.1 and 8.2. Okay, so let's get started. First we'll talk about general IC design philosophy. Now I just want to clarify what I mean before I get into the details of this. What we're focusing more on in this class is the circuits that are integrated, that is, integrated onto a single chip. We call these integrated circuits. The design philosophy tends to be a little different than if you're doing this on a circuit board. In that case, you're dealing with discrete components. Now, the circuit techniques, a lot of them are all very similar and translate over, but there are certain concepts and ideas that are specific to integrated circuit design, and that's what we're talking about here a little bit more. First, when you're dealing with integrated circuits, cost is very important. If you're trying to build a company and your company makes an integrated circuit and you have a competitor that's building a very similar product, it's important that your chip is going to be cheaper. And it turns out cost is proportional to area. So the larger your chip is, the more expensive it's going to be. So smaller is cheaper. So in general, when we're trying to design chips and trying to design circuits, we want to make them as small as we can. And we'll see how that translates here in a little bit. Keeping along those lines, transistors, especially modern transistors, tend to be very small and cheap. So if there's a situation where you can replace components with transistors, that's generally a good idea because they tend to be cheap. Other components are not as easy. Resistors, for example, tend to be large and difficult. And what I mean by difficult is a couple things. One, they take up a lot of space. And two, there tends to be a lot of variation between the resistors. And so this makes them a little hard to do on chip. Resistors have a big impact on bias circuits, as we'll talk about later in this lecture when we talk about the current mirrors. And whenever possible, it's best that we try to replace current mirrors with try to replace resistors with transistors. So because transistors take up a lot of space. Later in this class, when we move on to compensation, I'll show you an example of doing just that. Another expensive component are large capacitors or large capacitance. This tends to be expensive. Small capacitors are pretty cheap and easy and very common, but if you're trying to build big capacitors, it doesn't work so well and too expensive to do on chip. So again, you want to get around this. Other examples of this might include things like inductors. Inductors tend to be very large on chip and costly. So there's been a lot of push recently to get rid of inductors. That's more for higher frequency. Some other things to keep in mind, the supply voltages, especially on modern integrated circuits, tends to be a volt or even lower. So you're not dealing with a lot of voltage here. This can make the designs tricky. When we're dealing with transistors, MOS transistors, we have control over W and L. And this means a couple things. We can control our circuit, but it also means we can try to keep W and L small so that we can keep costs down. And finally, I want to introduce the concept of matching. So what is matching? Matching is when you lay out a device, say a transistor or any other capacitor, and if you put down two identical transistors and then you measure their current voltage characteristics, they're going to be a little different. And we call this how well they match. And with all components, there's variation. And this can include on-chip variation, or if you put down two transistors right next to each other, they vary slightly. It can include chip-to-chip variation, where if I take two chips from the same wafer, they're going to have different characteristics. And also there's wafer-to-wafer variation. So now we're trying to design the same circuit, but on a different wafer, and now we have different levels of variation. So this matching is something that we don't often think about in typical circuits, but it's very important in integrated circuits. Okay, and with that, we're going to move on and introduce current mirrors. But before we introduce current mirrors, I'd like to introduce the concept of a diode. Now, you've probably heard of a MOSFET diode in in 323. But just in case, this is the circuit configuration here on the left. And so what do you see? Well, it's a transistor where the drain and the gate are shorted together. So it's kind of a two-terminal device and acts very much like a diode in that case. So with the drain and the gate connected together, right, if there's current flowing through this, it's always in saturation, right? Always in saturation if it's on, right? Because the VDS is going to be greater than VGS minus VT, right? Now, if we want to look at the, or it could be off, could be in cutoff if the VGS minus VT, if VGS is significantly lower than VT. So it could be in cutoff or in saturation, but would never be in triode. Now, if we want to look at the small signal behavior, we should draw a small signal model. And what we'd see in this case is now we're going to short the drain. So we have GM, VGS, right? And we have our RDS. And so, and then over here, we have VGS. But notice that the drain, the gate, and the drain are now shorted, right? So it's really a two-terminal device. And we can see by inspection then that in terms of the resistance, this becomes 1 over GM in parallel with RDS. And typically, 1 over GM is much smaller than RDS, so this is approximately equal to 1 over GM, which tends to be a small value, typically on the order of hundreds of ohms or a kilo ohm, in that low kilo ohms. So this generally has what we call a low small signal impedance, right? And this is going to be important for, again, for circuit design to know that it has a low impedance. So this this diode is essential to our current mirror. Current mirror is what we see in the circuit here. So first of all, we have a diode connected transistor Q1 on the left side, right? That's transistor Q1. And then we have a second transistor Q2 on the right side. And notice that the sizes are labeled W over L1 and W over L2, signifying they can have different sizes, or W over Ls. And we've labeled the current on the left side I1 and the current on the right side I2. Notice the current on the left side is coming from some ideal current source, which we'll talk about a little bit later. So the first thing we can notice here in the circuit is that the two transistors have the same VGS. Right, their gates are connected together and the sources are both connected to ground, therefore the VGS is the same. And so we can write then that VGS1 is equal to VGS2, right? And then we can write down the current equations as well, and we can say, well, ID1, the current in I1 is equal to 1/2 mu n Cox W over L1 times VGS minus VT, and ID2 is equal to 1/2 mu n Cox W over L2, should be squared, sorry, times VGS minus VT squared. Now we want these transistors to remain in saturation. We know Q1 is going to stay in saturation, right, because it's diode connected, as we discussed earlier. Now in terms of Q2, we need the output voltage to remain greater than VGS minus VT for this to stay in saturation. So if the output voltage here, V out, goes too low, then transistor Q2 can go into triode. So we need it to stay sufficiently high. So this is a current mirror here. One thing I really want to point out is that if you look at this node here, and you're thinking, why do we have to have that diode connection? And the reason is that if we didn't have the diode connection, there would be nothing setting the potential on the gates. In other words, it would be like a floating node, and there's no way to set the VGS. So the diode connection allows a low impedance connection to the gates of Q1 and Q2, and therefore we can set the VGS through Q1, and therefore control the current in Q2. Okay, so moving on in our current mirrors. Let's do a little bit more analysis and try to figure out what I2 is relative to I1. So we just wrote down the current equations for I2 and I1. Those are equal to ID2 and ID1. So I could write that I2 over I1 is equal to 1/2 mu n C ox W over L1 times just VGS minus VT squared divided by 1/2 mu n C ox W over L2 times VGS minus VT squared. Notice that the VGS minus VT squared terms will go away, so will the 1/2 mu n C ox, and we're left with I2 over I1 is equal to W over L1 divided by W over L2. Or in other words, I2 is equal to this ratio of W over L's. I screwed this up a little bit, so let me just correct it. This should be W over L2 on the top, and this should be W over L1 in the denominator here. So that would mean this would become 2 and 1, and then this would become 2 divided by W over L1 times I1. And that's how a current mirror works. So if the W over L's are equal, if W over L2 equals W over L1, then we can say to the first order that I1 would equal I2. And what we see here is that I2 can be scaled by changing W over L2. In other words, if we increase the size of W over L2 relative to W over L1, we can get more current into W over L2. And this is how a current mirror is behaving. So we think of this as the current I1 gets mirrored into the current I2, hence the name current mirror. So in terms of current multiplication, effectively we can scale currents by simply scaling W over L's. And so in this example here, if we scale our current here on the right side by alpha, then the current would be alpha I2. And this also works for PFETs, not just NFETs, as we're showing on the right here. And we can see that, again, in this example, if we scale our W over L by alpha, then our current scales to become alpha I1. So this should be alpha I1 here. Okay. So that's just an effective way to move current around and to scale current at the same time. And now this one of the beauties of this technique is that you can use it in discrete devices. There are certain devices these days that you have to lay out integer multiples of the device. So in this example, if we have to use integer devices, we can use integer multiplication. What I mean by integer devices, if we have to copy this one transistor, we don't have control of W over L in this case, we can just lay out 3 identical transistors in a row. And in this case, what we'd get then is 3 times I bias. And there are certain situations where this is a really clever thing to do. For one, this is better for matching, right? And why is that? Well, if these transistors are laid out as identical, then our matching is going to be better between them, and we're going to get closer to exactly 3I bias than if we laid out one bigger transistor with a longer W over L. So that's one reason you might want to do this integer sort of multiplication. Now, what about the non-idealities of this technique? One thing to keep in mind here is that we sort of glossed over an important point, and the idea that the point here is the effect of channel length modulation. So what we've assumed is that I2 is going to equal I1 because, as you noticed in the beginning, we did not include lambda in our current equations. If we include the effect of channel length modulation, then we're going to find that I2 and I1 are not exactly equal. They're close, but they're not exactly equal. So how, as designers, might we try to avoid this? First, let's try to understand what the problem is. So if we look at VDS2 on the right side compared to VDS2 on the left side, they're not necessarily going to be equal. VDS1 on the left is going to be equal to VGS, right, because it's direct connected. But VDS2, the one on the right, is free to move around depending on what's happening in that circuit. So if we look at our ID versus VDS curve for these transistors, say, and we put in, let's just sort of arbitrarily mark here, VDS1, then that would have some corresponding current, which we'll call I1. Now, if VDS2 is not equal to VDS1, it might be out here, for example. And we can see that the corresponding current would be up here, and this would be I2. So you can see in this example that for this particular transistor, I2 and I1 are going to be different. So what we'd really like to be able to do is minimize this dependence on VDS. Right? If we have this dependence on VDS, then the only way we can make I1 and I2 equal are if the VDSs are the same. And in practice, we have a hard time controlling the VDS. So what do? What's the solution? What we can do is we can try to minimize this difference. And so first of all, how would we do that? Let's look at the current equation. We can write that ID is equal to 1/2 mu n Cox W over L times VGS minus VT squared times 1 plus lambda VDS. And as you know, this lambda term right here, right, dictates or models this change in the slope here of our curve, right? So what we'd really like is for this to be very flat, right? This transistor response to be very, very flat. And that means we want lambda to be small. Turns out that lambda, this channel length modulation term, is proportional to 1 over L. So long L means small lambda. And if you think about where channel length modulation comes from, where the channel length is actually changing as a function of VDS, the longer and longer your transistor gets, the smaller the effect is going to be of that channel length modulation. So long L is good for these types of current sources that we're dealing with here. So if we had a very long, if we wanted to sort of plot this qualitatively, what we'd see is something like this. We have this IV curve here. This would be ID versus VDS. That's supposed to copy the blue curve. And we'd have a curve that looks like this, super flat. This would be a long L. and a curve that would come up really fast. This would be a short L. So in terms of getting I1 and I2 to match, we want the long L so that lambda, or the effective channel length modulation, is minimized. Now we can quantify this effect, and we can, if you go through the math, we'll find that I2 is approximately equal to I1 times W over L two divided by W over L1 times 1 plus lambda times V ds2 minus V ds1. Now, notice that V ds1 is just equal to VGS, or VGS, and V ds2 is equal to V out. And this is equation, just for your reference, 8.10 in the book. And as you remember, lambda is equal to 1 over the early voltage. So they use the early voltage in your book as a reference. Okay, so in terms of how we might apply these current sources or this current mirroring, one of the beautiful things about using MOSFETs is that you can do this current mirroring all over your chip. And the reason is that there's no gate current, or very little gate current, in MOSFETs, and unlike BJTs, for example, that have a lot of base current. And so we can mirror this. And in this example here, you can see I1 gets mirrored over here to I bias. I bias then gets mirrored through this PFET over here, and it gets mirrored over here. And then the PFET can get mirrored back again through this diode connected device to this NFET on the right, and so on and so on. And in fact, in practice, this is really what's done. We start out with some current source, I, and then this gets mirrored over the entire chip. And you only have to make one current source in that case to mirror it for the entire chip. Okay, so I guess the question, last thing I want to talk about in this lecture is, where does this current source come from, right? So how do we generate that initial current source? Until now, I've just been writing it as an ideal current source, and as you know, ideal current sources are not possible, right? We can't actually make an ideal current source. So what do we do here? One way we can solve this problem, we can imitate a current source, is by putting a resistor in. So if we put a resistor in here, called it R, connected that to VDD, right, we could find then, just by inspection here, that I1, this for I1, would be equal to VDD. What's the voltage across the resistor? It's VDD minus VGS1 divided by R. And so this I1, this sort of becomes our current reference for the entire chip. Now, a couple things to notice about this equation. It depends very, very strongly on R, obviously. So you'd want R to be as exact as possible. When you're designing these circuits, you want your currents to be very exact because that's how they're designed. So you would need R to be very exact. If you were to put this resistor on chip, you'd be suffer from variation. In fact, when you build a resistor on chip, the variation is sometimes 10 to 20%. So that is not very exact. So in practice, if you use a resistor, it's typically off chip. Now, if you want to bring this current source on chip, there are techniques, a lot of interesting circuit techniques to generate this type of current on chip. They're a little beyond the scope of this class, but I just want you to know that you can do this on chip without having to rely on this external resistor. But the external resistor is, in fact, one way to make an off-chip current source and then bring it on chip. Okay, that's it for lecture 6. Thank you very much.